afternoon. I am Shailesh. I work in OpenSearch specifically on the indexing performance. And today I'm going to talk about this constant time aggregations using something called a star tree index in OpenSearch. So yeah, let's begin. Okay, so let's first talk about the problem. The problem is that the aggregation latency scales linearly with document count. So what happens is that dashboard queries scan every matching documents, and the aggregation latency scales linearly with it. So the more number of documents matching, the slower the query will be. So let's look at this query pattern. Here we have status equal to 200. Status equal to 200 has 200 million matching documents and takes 4.2 seconds. On the other hand, status equal to 400, status equal to 400 has just 3000 matching documents and takes just 5 milliseconds. So same field, status, same query pattern, just a terms query with a metric aggregation, and we have wildly different performances here. So if you think about it, like if you're a user building a dashboard, you'd want similar latency for similar type of queries, right? But that is not the case today. So some dashboard panels might be slow, but some others might be fast. So the goal is to achieve that O1 flat line. So that would be constant time regardless of the query. So okay, so let's talk about how the existing solutions fall short. So there are basically two current existing solutions for this. The first one is indexing rollups and transforms. So what this is that it basically pre-computes or pre-summarizes your data. But the problem here is that it is heavy. It competes with our active indexing workload, and it is not real time. So there is a lag before the query data is available. For modern day infrastructure, this delay is not acceptable, and it requires a separate management and scheduling as well. Other than that, the second existing solution is are the all aggregation specific optimizations already there in OpenSearch. But those optimizations only apply to very limited cases like match all or dog count, and they do not help with complex multi-field queries or nested aggregations. So yeah, we need something which is real time, which is built in line with indexing, and that works across multiple fields. Okay, and that is the star tree index. The main idea here is that we want to shift the performance from document count to the field cardinality. So how many unique values do your dimensions have? That is what should determine the speed, not the total document count. Okay, let's talk about one more on what star tree index is. So star tree is basically a multi-field indexing technique inspired by Apache Pinot and star cube research. What it does is that it stores pre-computed aggregation results like sum, max, min, averages directly in the index. It is built automatically during indexing, so no separate processes, no batch jobs. It is always in sync with your data. It is always up to date, and yeah, you can also configure and trade space versus time using a parameter called max leave docs. We'll talk more about this parameter in the upcoming slides, but yeah, the key insight which is that the performance should depend on the field cardinality and not the document count. So you should query 200 million docs in the same time as 3000. Okay, so let me walk through a concrete example so that this makes sense. Here, let's say we have 8 HTTP log documents. We have 3 fields: method, status, and size. Now, method and status are the dimensions, and size is a metric. So dimensions are the things which we want to filter or group by. Size is the thing which we want pre-computed. So in this case, we want the sum of size. That is why size is a metric here, and method and status are the dimensions. So now, let's say if I want to run this query, sum of size where method equals post. So what would the default method be? We would have to scan all the docs where method equals post. So that would be docs 4, 5, 6, and 7 in this case. Then we will have to sum up the sizes for all those 4 docs. That would be 800 plus 600 plus 50 plus 70. That would be 1520, right? So this doesn't sound bad with just 8 docs, but like let's say you had 400 million post requests. What would happen then? You'd scan all 400 million matching post requests. You would have to sum up the sizes values for all those 400 million documents, and that is where the seconds come from. So let's see how star tree makes this fast. Okay, let's understand how do we create a star tree first. Okay, so we have a root node. That root node would consist of all the documents. So there are a total of 8 documents in our example. So the root node will have all the 8 documents. Now, the root node will have basically we'll group by the total number of unique values for the first dimension. The first dimension here was method. So we'll see the total number of unique values of method which we have, that is get, post, and put. The first 3 documents have method get, the next 4 have post, and the last one is put. So so there are 3 children for the root node, that would be get, post, and put. Now remember we had 2 dimensions, right? Method and status. In the first level, we are just grouping by the first dimension, which was method. Now, step 2 would be to split by the status and then store the metrics. So we have a root node, we have get, post, and put. So this is the same as before. Now under get, what we have is that we'll basically divide it further into more nodes, and the children of get would be the total number of unique values for all the documents where method equals to get. So the total number of unique statuses for documents which have method get would be, so first 3 documents have method get. The first 2 documents have method get with status 200. The third document has method get with status 404. So there are total 2 unique values for the status where the method is get. So it'll have 2 children, 200 and 404. Similarly for post, the documents 4 to 7 have method post. The 4th and the 5th document have method have status 200. The next 2 have status 500. So post will have 2 children, 200 and 500. Again, put will have just 1 child, 200, and yeah. So the sum 800 for the root get 200 is coming from the first 2 documents. That would be 500 plus 300. Because we have 2 documents, we'll store count as 2. Similarly, root get 404 will store sum 100 because the third document has size 100. It just matches 1 document, so we'll store count 1. Similarly for post and put as well. Okay, so the idea here is that each leaf stores 1 pre-computed star tree document. Now, if you want to find out the total number of documents where, let's say, method equals get and status is 200, what would happen? We'll start from the root node, then we'll go to the get node, and then we'll go to the 200 node. We'll directly get sum equal to 800 in just a single read. So it wouldn't matter if there are millions of matching documents for get 200 or just 2 documents in this case. We would just have to do just 1 single read. Okay, so now let's say we want to find out the total number of documents where method is, let's say, get, and status can be anything. What would we have to do? We would have to go to the root node, we'll have to go to the then we'll have to go to the get node, then we'll have to sum up the sizes in the in all the children for get, right? That would be 800 for the 200 node and 100 for the 404 node. So the total size would then be 800 plus 100, which is 900. So we are still scanning all the children nodes, right? So now what we have is star nodes. So if you see from the root node, now we have a red box star. So this star is where the name star tree comes from. Okay, so basically for root node, if we have more than, so root node was split into get, post, and put previously. So if we have more than 1 children for root, we'll add a new node which will be called as the star node. So now this star node will comprise of all documents get, post, put. It wouldn't matter what the method is. So again, from root to get, we again have 3 children, 200, 404, and again a star node. So what that star node would mean? That would mean that all the documents which have method get, but status can be anything. So we'll store a sum of 900 there. That 900 is coming from 800 plus 100. Similarly, root post star would mean all posts regardless of status. We'll store a sum of 1520 there. That is 1400 plus 120. Similarly, for the star node as well, the star node would again have a child star. That would mean all docs, irrespective of method or status. So if we have a query of something like, let's say, sum of size, my method equals post, what would happen? We would traverse the root node, we would go to the post node, and then we would go to the star node. So the answer would be 1520. And this is just a single doc read. It wouldn't matter if there are like millions of documents matching method equals post. We would just get our answer in just a single doc read. Okay. Okay, yeah, so this max leaf docs parameter. So we talked about this in the previous slides. This was basically for basically trading space versus time. So this controls when do we have to stop splitting the tree. So if max leaf docs is 1, we'll stop splitting until we have just one leaf in our, basically we just have one doc in our leaf. So every query would just go to one pre-computed doc, and this would be the fastest because for every query we would just have to make one read. But this will have more star tree nodes and hence more storage. So if max leaf docs is 1, it will have the best performance, but the storage will also be higher. As in when you increase the max leaf docs, what happens is that you take less storage, but then you'll have to, in the worst case, you'll have to scan those many number of leaves, those many number of docs in the worst case. So max leaf docs equal to 100 would mean that we should stop splitting until a node has reached 100 or fewer documents. So yeah, again, yeah, the query could scan up to 100 docs. This is less storage, but again, 100 docs is still thousands of times better than scanning millions of docs, right? So yeah, the lower and faster query is more storage, higher and less storage, and slightly more scan. So this is the trade-off parameter which we can configure to, yeah, for space versus time. This is what we can configure. Okay, using star tree. So using star tree is very simple. We just have to add the configurations, the dimensions, and the metrics in the composite config. So in this case, dimensions are the things that we want to filter or group by. So in this case, this is method status and then timestamp rounded out to R. Again, metrics are things which we want to pre-compute. In this case, it is average of latency and some average max of size. So yeah, we just add this to the index creation. There is no change to the queries or bulk ingestion. Everything stays the same. But existing queries get optimized. They take the star tree flow, and that is it. Yeah. Okay, so let's talk about how queries actually execute under the hood. Okay. So let's say we have a query like this. Uh, this is a query in which we want to, let's say, find out the average size for all docs where method equals post and status is 200. So in the default approach, what would happen? In the default approach, we basically do this query in two phases. In the first phase, we call this as the query part. What would happen is that we would use fast Lucene structures like inverted index or BKD trees to find out the matching document IDs where method equals post and status is 200. So this part is fast, wherein we find out the matching doc IDs for the given query. Now the next part is the aggregation phase. In the aggregation phase, we'll have to iterate through all the matching documents. So we'll have to iterate through all the matching documents and then aggregate the size field for all those matching documents. So this part is the bottleneck. Let's say there are like 200 million matching documents. You'll have to iterate 200 million times, get the size field from the doc values, and then basically sum them up. So this part is the bottleneck. And this is the reason because of which the query is slow. Okay, so now we'll see what happens in the star tree case. So in the star tree query execution, what happens is that we have the same query, but it takes a different path. So we convert the query to what we call as a star tree filter. So star tree filter is basically a filter because based on which we traverse the tree and we follow only the matching dimensions. So here what we do is that we collect the pre-computed docs, which would be far fewer than the original, and then return the result. Okay, let's talk about it more in the next slide. Okay, so now there are like, let's say there are four types of star tree filters. Let's discuss on the first one. The first one is the terms query. So let's say we have a term query like method equals to post. So now method equal to post, that what would happen in the star tree case? In the star tree case, you would just go to the post node at the method level, and we would basically ignore all the other nodes for all the other methods which we have. Like, let's say if we have method equal to put, method equal to get, we won't care about that. We can directly prune it. So method equal to post is what we care about. That becomes an exact match filter. Again, let's say we have a range match filter that translates to a range query. Let's say we have a range query like status is between 200 to 400. So what would happen in the star tree case? You would only care about the nodes which have status between 200 to 400. We won't care about all the other nodes. We can directly prune them. Again, if we do not have any filter on a particular dimension, that would translate to a match all query. And what that means in terms of star tree is that because there is no filter on the particular dimension, we can directly use the star node. And yeah, the last one is just the match none filter, which is used when taking the star tree path is not possible. So yeah, basically the main point here is that the latency is independent of the doc count. It only depends on how many dimension combination filters match your star tree filter. Okay. And yeah, one more thing here, that this basically the things you want to pre-compute, like let's say here size, we'll have to also give the aggregation which we want here. So like if you want to pre-compute average, we'll have to give sum and count so that we can compute average. Okay, so yeah, let's talk about Boolean queries. So it's like real world queries would have multiple combinations of different types, right? So real observability queries would combine and or operations together. So let's look at this query. This query says that we want to find out or aggregate the total bytes where the status is between 200 to 400 in the 15th hour. So the first range in the must clause is that the status is between 200 to 400. The second is that the timestamp should be between so timestamp should be on the 1st of June 1500 till 1st of June 1600. That means the timestamp should be on the 15th hour, and the method should be get or post. So this or is a should clause inside a must. So before we had the support for Boolean queries, a query like this would have fallen back to the full scan. So now let's see how we do this in star tree. Okay, so basically in star tree filter, what we have is that we have for every level or every dimension, we have a star. We have this get comma post. We have for status we have 200, 400, and for timestamp we have 15 to 16. So for every dimension we'll have a filter. So what this means is that let's say for method would correspond to an exact match filter, which means get comma post, because in the query we had a should clause where method was either get or post. Same for the status, that will correspond to a range match, because in the query we had a range query on the timestamp field. So the status would on the status dimension we'll have the range match filter. Again, for the timestamp, that will again be a range match, because we want to find out the nodes which have timestamp between 15th to 16th, or all the documents on the 15th are on 1st of June. Okay. So now here we have the root node. We have let's say 4 children: get, post, put, and star. Now we want to get the methods where we want to get the documents where method is either get or post. So the put path is pruned, because we do not need documents which have method put. So the only two valid paths right now are root get and root post. Now under root get, we will again apply our filter. Under root get, we can only have status between 200 to 400, 200 inclusive, 400 exclusive. So 200 yes, 404 no, it will be pruned, and star will again get pruned. Similarly for post, 200 yes, 500 will get pruned, and star will also get pruned. Same for the 200 node as well. It has, let's say, two children, 14 and 15. We only want timestamp in the range of 15 to 16, so we'll prune out the 14 and the 14 from the next path as well. So basically, we have only two valid paths: root get 215 and root post 215. So even if there would have been millions of matching documents, we could answer this particular query by just reading two reduced star tree documents. So in the first reduced star tree document, we have a sum of 4200. In the second reduced star tree document, we have a sum of 8100. And 4200 plus 8100 would be 12,300. In just two docs read, we can answer this whole query. And yeah, this is the same thing. We read two docs, we skipped everything else at each level. And at scale, this would mean that we have the same two reads, whether there are millions of original documents behind those nodes. Okay, so date histogram. Date histogram is the number one observability query, wherein we want to, like, let's say, ask, show me metrics per time bucket. In this particular query, let's say you want to find out the total bytes and the average latency for, let's say, per hour. So what would happen here? So let's say there are a billion documents and we want to we want to bucket them by hour over a 30-day period. So for 30 days, there would be how many buckets? 30 times 24, that would be 720 hourly buckets, right? And there are billion documents, so every bucket could have millions of documents. So we'll have to, in the default path, we'll have to basically check each document and then figure out which bucket it belongs to. And then for every bucket, we'll have to sum those values up. So at scale, this would be very slow. Let's see what happens in the star tree case. So in the star tree case, every timestamp is stored as a dimension rounded out to the configured interval. So in the previous query, we had a calendar interval parameter here. This we set it as R. So in our case, we were rounding it off to R. So similarly, if the original timestamp was, let's say, 1423, and that would be rounded off to 1400. Even if it would have been 1458, that would have been again 1400. For a timestamp which would have been 1502, that would be stored in the tree as 1500. So each unique rounded timestamp would mean a node in the tree with pre-computed metrics. So yeah, so now we discussed there were 720 hourly buckets, right? So that would mean that we'll have to do just 720 star tree doc reads. So even if there are billions of documents which are present, we'll just have to do 720 star tree doc scans. We can compute the basically the average for those. We have the sum stored, we have the count stored, we can divide both of them to find out the average latency. Similarly, for the total bytes as well, we can do a similar thing. Okay, so this is the last query which I want to talk about. This is the nested aggregations query. So real dashboards are not just one simple filter, right? They combine they have multi-level fields and multi-level breakdowns. So let's say we have this query, we want to find out the average latency per method for each hour. So here the first query is date histogram. Under that we have a terms query. Under that we have a metric aggregation query on latency. So what we want here is that for each hour, we want to group by the HTTP method and then find out the average latency for that particular group. So there are two levels of bucket nesting here. First is a date histogram, second is the terms, and the third is the metric. So yeah, before we added to the nested aggregation support, this would have fallen back to a full scan. Let's see how this works in the star tree case. Okay, so yeah, so basically, let's say we have configured the star tree with the first dimension as timestamp and the second dimension as method. So what is happening here? Here, basically, we have already divided the docs in such a way that uh, for every timestamp rounded out to R, and for every method, we have the pre-computed metrics already stored. So each leaf is one pre-computed doc. So let's say there are total 2 hours and 3 methods in this case. We just need to do 6 docs read to find out the nested aggregation output. So for all gets in the 14th hour, we'll have the average as 150. For all posts in the 14th hour, we'll have our average as 166. Similarly, for all posts in the 15th hour, we'll have the average as 180. So we can basically find out the total nested query output because of this. And yeah, on benchmarking, this was 5 to 300 times faster for nested aggregation queries. Okay, so let's come to the benchmarks. Okay, so the first point is about the predictable performance. So here we have basically decoupled the latency from the document count. So this was the example we discussed in the initial slides, right? We have the same type of query, a term query with a metric aggregation, where for status 200, we had 200 million matching documents, and that was taking 4.2 seconds. With star tree, this would take 2.5 milliseconds. Similarly, for status 400, we had 3000 matching documents, and that was taking 5 milliseconds. For the star tree case, this would take just 2.7 milliseconds. So if you look at the star tree column, 2.5 milliseconds, 2.7 milliseconds. So both are similar, right? So that is what we wanted to achieve, irrespective of the total documents which match. For status 200, there were a lot more documents which were matching 200 million, and in status 400 there were very less. But irrespective of that, the performance is similar. We just have 2.5 milliseconds and 2.7 milliseconds. So both queries have similar latency, and that is the point of using star tree in this case, predictable performance. Okay, so now about the throughput improvement. So now, because existing queries are already fast, we can now run more concurrently. So even in the best case, like we have, let's say, 1 billion documents with low cardinality fields. So now, because the dimensions have low cardinality, the star tree will be smaller, because the star tree splits based on the total number of unique values in a particular dimension, right? So if the cardinality is low, that would be our best case, and we have seen up to 1,000 times performance improvement there. And even in the worst case, there was still a 40% better latency. So the worst case would be the examples where the cardinalities are very high. So let's say we have a column user ID. So a user ID is a field which would have very high cardinality, right? So if you now for user ID, if you provide user ID as a dimension on star tree, the tree would split on every unique value of user ID. So the tree will become huge. So because of which we'll have to scan more, and then the performance improvement will not be that much. So so in general, we should only choose fields, or we should only choose dimensions for star tree which have low cardinality. Okay, so coming to the advantages and caveats here. Okay, so the advantages are something which we discussed. The performance is predictable. We have a constant time performance irrespective of the documents which are matching. We have a native multi-field support. Because of the way star tree is designed, it works across multiple fields. It is real time. It is built during indexing. There is no separate batch jobs or anything which you have to do. It is storage efficient. So based on basic common configurations, like let's say we basically choose dimensions which have medium to low cardinality. This we have just seen a 1 to 2% of storage overhead there. But yeah, that would increase if you add dimensions to the star tree which have very high cardinality, like user ID, IP addresses. So these will have high cardinality, and hence the storage might go on a toss there. Okay, so the next is fraction of IO for queries. So yeah, it takes very less IO for queries. And the last one is that it is seamless. You do not require any query changes. Existing queries automatically start going to the star tree flow. No changes in bulk or anything. Okay, so now let's talk about the caveats. The caveats is that it is currently append only. So the deletes and updates are not supported right now. The indexing throughput impact. Yeah, so there will be indexing throughput impact based on the configuration. Uh, Again, it's inefficient with high cardinality fields because the star tree size will get bloated up. Then the last is that, yeah, there is a limited aggregation coverage, which is still growing on as we build on working this. Yeah. Okay, so yeah, let's talk about two more aggregation types, percentile and cardinality, which we explored. So, okay, so percentiles first, let's talk about. So like P50, P95, P99 latencies are there on every dashboard, right? Uh, so the main challenge here in supporting percentile aggregations using star tree is that percentiles cannot be like aggregated in the same way like you can a sum. Like two sums can be added together to get a correct larger sum, but two percentiles cannot be uh, averaged out together to get a correct percentile, right? So the solution here is to use something called a T-digest sketch. So T-digest is basically a data structure that compresses a distribution into a small sketch, and two sketches can be merged together to get accurate percentiles. Um, so what is the problem here? The problem is storage. So okay, so for basic metric aggregations like sum, in every star node or in every star tree node, we would only have to store about 20 bytes to store that particular sum. But what happens in the T-digest case? In T-digest, we benchmarked it and we found out that for every node, it as and when the documents start to increase, it reaches up to 2 to 4 kbs per star tree node. So now let's say there are a total of million star tree nodes in your data structure. That will correspond to a million. That will correspond to x GBs of extra storage just to calculate percentile aggregation. So which is bad. We can't have GBs of extra storage just to calculate percentile. Similarly, for cardinality aggregation as well, we have the same problem. Cardinality would mean the total number of distinct values your dimensions have. Same case here. You can't add two distinct counts together to get a correct distinct counts because there might be overlaps, right? So, um, okay, so the storage problem is even more stark here. If you see the every HLL object takes around 11 kbs per node. So it doesn't matter if you have one document or a million documents, it will still take 11 kb per node. So again, if you think about it, let's say you have a million star tree documents. That would correspond to 11 kb times a million. That would be 11 GB just for calculating cardinality aggregations. So yeah, so this is something which we do not want. So yeah, so we have made a practical decision here that we have benchmarked both of these things thoroughly. Uh, and right now we have parked them out for now. But yeah, but the door is open. We can so if users are willing to trade that extra storage for constant time percentile or cardinality aggregations, then we are willing to support it. So yeah, we can support uh, if yeah, if users are willing to trade off that space versus time. Okay, so now retroactive star tree upgrade. So until recently, star tree had a limitation that it could only be enabled at index creation time. So if you had existing indices with historical data where you had terabytes of data, you couldn't that index couldn't benefit from star tree without the need of without reindexing. And reindexing is a very expensive operation. If you want to reindex an index which has, let's say, terabytes of data, that will take that would be a multi-day operation. So what we built was a per segment upgrade solution. Here, what happens is that it works in three phases. The first phase is the mapping update. In the mapping update, we add the star tree configuration to the existing index. In the phase 2, we built the star tree per segment from the existing doc values. And in the phase 3, we rewrite the segment data and then reopen the engine. So on an existing index, we upgrade it to a star tree index so that we do not have to reindex and the queries which come henceforth can use the star tree flow. The result is that, yeah, for let's say 181 million documents with an index size of 12.7 GB, it got upgraded in 6 minutes. Reindexing the same would have taken hours. So yeah. Okay, now let's talk about the operational lessons here. The first is the append only constraint. So there are no deletes and updates supported after star tree is enabled. That fits observability or logs workloads perfectly, because we usually do not want deletes or updates happening there. But yeah, so okay, so I'll explain a bit as to why deletes are not supported. So like let's say we have a metric sum and we have a document which had uh, let's say we have a document which had a value 5. Now if we are deleting that particular document, we have to negate that particular value 5 from all the nodes which have this document. So that would in the end be directly proportional to the number of deleted documents. And you cannot do this for every type of metric aggregation, right? Because for max and min, it'll not be possible to negate by going through every node. So currently we do not support updates and deletes. Second, yeah, I think we talked about this, that the cardinality matters. High cardinality dimensions would create huge trees. So yeah, we should, so like let's say for timestamp, if you put timestamp as a dimension in your star tree, we need to also configure the interval as to uh, which interval it should be rounded off to. We can provide seconds, hours, or days, years as well. And yeah, we should only create star tree on low to medium cardinality dimensions. Things like IP addresses, user IDs, and all should not be provided to a star tree dimension. Again, storage is predictable, 1 to 2% overhead for typical configuration. It scales with cardinality, not doc count. No query changes needed. Existing queries auto-optimized. Star tree is transparent. It bridges the gap between search and OLAP. So sub-second analytics on a billion scale datasets without the need of a separate analytics engine. Okay. Okay, so what's next? Multi-star tree support. So yeah, so we could have different trees for different query patterns instead of relying on just a single star tree field for every queries. So yeah, the second is the delete and update support. We could have it, but that could be still be limited to specific metrics. Again, more aggregation types. We are still working on expanding coverage for this and broader field type support. Okay, so this is the credit slides. Thanks to everyone who contributed to making this feature possible. And yeah, that's it. Thanks. I can take questions if any.
Yeah, exactly. Thank you very much.
Yeah.
Are there any questions in the room? Yes.
So throughout most of your talk, I had a question, but you anticipated it with slide 28. So I have a follow-up to non-numeric aggregations that you might want to track with this technique. Are you looking at techniques to make it more tractable beyond just saying only turn it on if you need it?
Beyond numeric, right?
Like a hyperlog log, tdigest, bloom filter, anything that you can sort of treat as a sort of thing that you can sum and
correct. So for terms aggregations, we have support. So like for non-numeric, like percentiles or cardinality aggregations, I think we talked about, like it would be a hit on the storage as well, because for percentiles and cardinalities, they cannot be aggregated in the same way like numerics can be, like sum and all. So that would take a hit on the storage, because for tdigest and hyperlog log.
Yes. The question is like, so you said you can only turn that, you'll turn that on only for special cases where the storage trade-off is justified, right? Are you
Correct.
looking at other ways to sort of reduce the cost by maybe abstracting more, or is there anything else you're considering in that space? That seems like a really interesting application here.
Okay, as of now, that is the only thing we have considered. Yeah. But yeah, I think.
All right. Any more questions? I don't see any hands up. All right. Oh, there's one. We have time for one last question. Here it comes.
So when the index gets, when you define the mapping in a way, the order by which you define the dimension actually then makes the tree levels, right? So you like when you were defining the dimensions, right? And then there is the order, for instance, method, then counts and so on.
Correct.
But internally, this then defines how the star tree looks like.
Correct. So we have to also define basically a sequence of dimensions based on which the star tree will get created. So what should ideally happen is that we, so let's say the first dimension should be the thing you most likely filter your queries by. So that would be like let's say the timestamp is there. So timestamp should be the, if timestamp is one of your fields, then that should be the first level of the tree. And similarly, based on your query patterns, we can configure the dimensions. Yeah.
All right. Thank you very much. Give it up again for our speaker.